Yep. Good evening, everyone. Session again. Let's start off. This was the last thing that we did. Let's start off with a question. Let's say we have a sealed container. We have a piston of area A. Here, this part is filled with 3p knot pressure. And here you have a block of mass M. This is filled with a liquid of density rho for height h. Then it is filled with another liquid for height 2h, but density is 2 rho. You're getting? So sealed container, the top part is sealed. You have a gas inside at pressure 3p naught. Then there's a mass, piston, and there are two different liquids. And this is point A. Find pressure at point A. Yeah, so I did mess up everything that is possible there. Instead of atmosphere, we have a sealed container with a pressurized gas at 3p naught. And we have a block placed on a piston which is pushing the liquid down. And there are two liquids of rho and 2 rho. Find the pressure at the bottom. Get this, it's an easy one. Let's see. Now look at this thing. So pressure at A. Let's just try to go one at a time. Due to this atmosphere, what will be the pressure? 3p naught? If nothing was there and only gas was there, it would have been 3p naught, right? Then what do we have? We have a block. What is pressure? Force by area. So how much force does the block give? mg. On how much area? A. So the block ka pressure is mg by area. Then the liquid is giving pressure rho gh. Then the second liquid is giving pressure 2 rho g 2h. Easy? You just have to find the pressure due to each one, and remember pressure is a scalar, it just adds up. Got this? Next one. That's an easy one. Suppose we have a container here. We have a container There we have three containers like this. All of them have same base area. Meaning this bottom part ka area is same. So here there is point A, here there is point B, here there is point C. Case 1, they're filled to same height. Case 2, they're filled the same volume. Matlab, in the first question, they're given same height. In the second question, they're given same, let's say, 5 liters in first one, 5 liters in second, and 5 liters in third. Same volume of liquid is filled. Arrange the pressures at ABC. Arrange pressure PA, PB, PC in ascending or descending order. Get this. I'll give you a minute. Theoretical equation mostly. In HSC, this is called a paradox. Let me tell you what is that also, but you give it a try. Let's see. First was easy. Like I said, the pressure depends only on the height. Case 1, since the height is same, we know pressure is equal to P naught plus rho GH. So PA is equal to PB is equal to PC. Like I said, it doesn't matter the shape of the container. If the height is same, it is there. Case 2, you just think about it logically. Let's say if you go to a shop to buy a cool drink, which glass will you take? Let's say the shop offers you this. They will fill up the glass. 10 rupees, they will fill the full glass. Which glass will you take to go to the shop? The C, right? If you're on dieting, you will take B, but that is the point. Getting it? So, meaning if you really think you'll get same thing, you should take your sister, give her glass B, you take glass C, and then go to the shop and see what happens. So if you put same amount of liquid, what happens? I'll just give you a shape. It's clear. If the first one, liquid is still here, the second one will definitely be more. The third will be much lesser. Does it make sense? This is H2, this is H3, and this is H1. So we can clearly see H2 will be greater than H1 is equal to H3. Therefore, PB will be greater than PA is greater than PC. Now the question, this is fine. From heights, it is fine. But the question comes this thing. Now in HSC, this is what they say. They say, since you kept same volume of liquid, listen carefully. Since you kept same volume of liquid, mg is same. And you also said the area is same. So from this logic, shouldn't the pressure be mg by A and shouldn't the pressure be equal? But you're saying from height, the pressure is not same. Did you get the logic? If you kept same volume of liquid, mass is same. And the area is also same. So force pressure is mg by A. That's not working anymore. Because it definitely, and we also said the height is more. So where are we going wrong exactly? What do you guys think? Think. I'll give 30, 40 seconds. Did you get what I'm saying? Area of the base is same, right? The force acting on the base will give you the, see, you want the pressure on the base, right, Ansh? Where are ABC? They're on the base. So it should find pressure on the base is the force acting on the base by area of the base. A isn't uniform, height of the center of mass. C can exert extra force. A varies with H. See, if I ask you force on a plate, what will you do? Pressure on a plate. Force acting on the plate by area of the plate. I'm asking you pressure on the base. So why are you taking area of the side and everything? You take area of the base. Any other interesting answers? Finding volume to find why you need to do all that? It is given the same volume, right? Same volume is given, so mass is same. And you also said base area is same. And from that logic, the pressure should be force by area. So shouldn't it be same? But it is not. Let's try to draw the FBD of the liquid and you will see. What you're missing is this. If you draw FBD of the liquid, the first one was like this, second was like this, third was like this. I agree, mg is same for all of them because the volume is same. But what you're forgetting, the container is also pushing it. This is the F due to the side walls. And here the container is pushing it up. And you can see by symmetry, horizontal components cancel, vertical components add up. So here the pressure PA will be mg by area because the horizontal forces cancel. Here pressure at B, so it is a net force that is mg plus F side walls by area. True. The thing is still the same, mg by force by area. But what is force? Force is not only mg. You have to consider the force due to the side walls also. Whereas pressure at C was mg minus force due to the side walls by area. Does this make sense? But if I ask you the normal reaction on the ground, then it will be same again. That is because the force between the liquid and the container becomes internal force. The normal reaction on ground, because that will be equal to mg only if you take the whole thing as a system. Is this making sense, everyone? Yeah. So the thing is, people forget the normal reaction due to the walls. We only think, okay, there's an mg and there is an area. Why is it not mg by area? Because the whole force is not mg. There's a side walls of force also. So this is what they call in HSE as a pressure paradox. If the weight is same, if the area is same, why is the pressure not same? Because there's a side walls. Clear with this? Decent question. Matlab it's a decent thing. If mg is same, why it is not same? Now let's see a question based on this. All clear with this? Any doubts? Arush? Adjust your camera a bit. Can't see you. Taksha? Clear? Devansh? Abhinav? Arya? Pratik? Parth? Clear? Sharman? Next one. We have a container like this. Height of the container was R. The bottom radius is R. The upper radius is 2R. Pressure is P naught. Filled with liquid, rho. Find the force due to the side walls on the liquid. So we have a container, so it's like a part of a cone, frustum. Is the shape clear, everyone? Get this. You got 2 minutes. And like I keep saying from the last class, what we are doing is simply FBDs, if you have realized. The only new thing is in the FBDs, you're also including the, instead of force, you're saying pressure into area. But literally, this entire thing, what we're doing today and last class was free body diagrams equilibrium. Get this, get this. Rho G. Dimensions not matching, right? Purva. Rho G is pressure, na? Draw the FBD of the liquid. Simple, see, like till now, whatever I taught you, don't forget whatever I taught you. In entire mechanics, you have only two set of weapons with you. Force and torque equations, conservations. It is still valid. I asked you to find the force due to sidewalls. You can't use conservation. You have to use FBD. Forces, the first thing you draw is an FBD. So Parth, according to your logic, you don't need area, you don't need height, nothing. Matlab, I can take any damn shape of container and your answer is constant, P cos 45. Is that what you're saying? I mean, they can take R infinity and the answer would still remain same. Come on, people, use Earth ka max and Earth ka physics. Please don't use your planet ka physics. I know you have come from a very highly advanced civilization, but please forgive our, mortal humans. We are not still that advanced. 7/3 RG dimensions are goofed up. Daksha, that is wrong. Let's see. Let's draw the FBD. Check your FBD. I don't know why you got this thing wrong. So from the top, we have atmosphere P naught into pi 2r whole square. From the bottom, we have pressure of the liquid is P naught plus rho GH into pi r square. This is the force on the base. The side walls are pushing this way. By symmetry, you can say the horizontal components will cancel. Only the vertical components will remain. So this is your F side walls. And your mg. That's it. There are four forces, everyone. Okay, let's see. So then, so F side walls plus P naught plus rho GH pi r square is equal to mg plus P naught into 4 pi r square. So if I can find my mass, my job's done. The F due to side walls is mg plus P naught into 3 pi r square minus rho GH into pi r square. So how to find mg? You can clearly see this was a part of a cone. So if you take a full cone whose radius is 2r, whose height is 2r, because it's 45 degrees, minus if you subtract this small cone whose height is r and the height is radius is r, then we will get this remaining frustum. Is this making sense, everyone? So the volume of that piece is a full cone minus a small cone, right? And what is the volume of a cone? 1 by 3 pi r square. R is 2r, h is 2r. This guy would be 7 by 3 pi r cube. Therefore, mass m will be rho into 7 by 3 pi r cube. Done. Take this and substitute here. You got your answer. Is that clear, everyone? So there'll be three terms there: mg ka term, p naught ka term, and the rho gh ka term. Please check where it went wrong. There are four forces on the FBD. I think most of you goofed up the FBD only. Again, what is this? This is not FBD of the container. This is FBD of the liquid. Just the liquid. So that side walls is the force between the liquid and the container. All clear with this? Next one. Next one. Turn in the page. Nikhil, clear na? Parth, Ishana, clear? Ansh, Vihan, Ignajit, Borona, clear? Next one. We have a container filled with liquid, P naught, density rho, height h, base area A. Alpha is coefficient of linear expansion of container. Gamma is coefficient of volume expansion of liquid. This is point A. Find the change in pressure at A if the temperature changes by delta T. So initially there is some pressure. Then you increase the temperature by delta T. Then the pressure would change. What is the change in pressure at point A when temperature changes by delta T? Thermal expansion and fluid mechanics, everyone. If this was a simpler question, mains level also, they would ask like this. If the temperature increases, what happens to pressure at A? Increases, decreases, depends on the value of alpha and gamma, can't say. So something of that sort. That would have been the theoretical options, but let's calculate only numerically. That would be a little more work. Rho gamma minus 2 alpha delta T, okay. Try, I'll give another 30, 40 seconds. The problem here is, think about it, when you heat it, the container expands, the liquid expands, liquid density changes, everything gets messed up, isn't it? Liquid density also will change, liquid will expand, height will change, base area will change, but something remains constant. What? Don't tell me P naught, I'll punch you. Say something more reasonable. What remains constant? I asked this yesterday and someone was saying that point A also remains constant. Arya, there is a better word for that, right, Puroja? Mass of the liquid remains constant, isn't it? No matter how much I heat, mass of the liquid remains constant. And we know pressure is mg by area. So can you think something from that perspective? Now try. I'll give another 30, 40 seconds. So if you see in terms of mass, it actually kind of becomes easy. Instead of rho g h, because rho g h, rho is changing, h is changing, it becomes very goofed up. Let's see. So initially, this area is a pressure is P naught. This is mg. So the initial pressure P initial will be P naught plus mg by area. And what is M? Mass is the density area into height h. That is the initial volume. Now, understand A changes, rho changes, h changes, but M remains constant. Now, when you heat this, at new temperature, the area becomes A into 1 plus 2 alpha delta T, areal expansion. Height of the liquid changes. I don't know. I don't need. But I'm pretty sure mg remains constant. So P final will be still P naught plus the weight is mg by A into 1 plus 2 alpha delta T. So if this was a mains level question, and if they ask you what happens to the pressure, you can be 100% sure whenever temperature increases, area will increase, mg remains same, pressure always decreases, isn't it? Independent of gamma. And that's the best part. It doesn't depend on gamma, you can be sure, because the area always increases if you increase the temperature for a container. So change in pressure delta P is P final minus P initial. Subtract them, P naught will cancel. We will get mg by area 1 by 1 plus 2 alpha delta T minus 1. You can send it up using binomial approximation, or you can just, this will be minus mga 2 alpha delta T by A into 1 plus 2 alpha delta T. For small alpha, you can ignore this. This will be minus 2 mg alpha delta T by area. Alpha delta T is much, much less than 1. Always check the options. Sometimes they will give this. You will get till here and you'll not understand what to do. They used binomial approximation. And kind of makes sense because 1 plus alpha delta T is derived under the assumption alpha delta T is very small. All got this? So if this was a mains level question, and if they ask you what happens to the pressure, if temperature increases, pressure decreases. That's it. There is no doubt about it. It doesn't matter what is the density, what is gamma, how is the height changing, everything is taken care of. All clear with this? That is your thermal expansion and fluid mechanics. This is what I keep saying. Unlike, maths and chemistry, where your chapter 4 and 5 are bad, your chapter 6 and 7 don't get affected. Physics is not like that. Every damn thing you learned before, everything will keep popping. It's an advantage and a disadvantage. It's an advantage for people, right? Because you're always on your toes. Every chapter is being revised in some form or the other. Disadvantage is because if you're not serious about studying and if you don't take things seriously and not doing daily work, unlike school, where you can cover up everything in last 1 month, you won't be able to do it. School, people used to be proud, I just studied for 1 month and got 90%. I must be some kind of genius. No, you're not a genius. You're just an idiot. You can't focus for long and study for long hours. So, yeah. Next one. We have a tall container filled with gas. Tall container meaning infinitely long. It is filled with an ideal gas. Constant temperature. The whole gas has a constant temperature. In reality, that is not true. Molecular weight is m. We also assume constant gravity. That is also not true. So we are doing a lot of assumptions. P naught is the pressure at bottom. So find the pressure at a height h from the surface. KTG and fluid mechanics. So we have a tall container. The entire container is filled with gas. Molecular weight is m. Temperature T is constant. Gravity is constant. At the bottom, the pressure is P naught. Density is not given. As you go up, pressure decreases because obviously weight is decreasing. So how does the pressure vary with the height? Get this. You got 2-3 minutes. Think for a minute, then I'll tell you a few things. Then I'll give you another 1 or 2 minutes. Anyone didn't get the question? Anyone, the data is not clear? So calculate, na, God. Use whatever law you want. Use Avogadro law, use Einstein mass equivalence, use everything. Use atomic structure, solve, I don't mind. Think. Again, never worry about the answer. It's okay if you don't get the question by after 3 minutes. That's not the point. If you get obsessed with every time, I need to get the question right, then you're looking at the wrong thing. You won't have fun in learning. Just think like you are getting something new to learn. Now, two things. See. First of all, I said ideal gas. If I use the word ideal gas, which equation is always there with you? PV is equal to nRT, right? So that's how you should always think. Okay, you said ideal gas, so means this is there. Second thing, one thing is clear. कुछ तो हो रहा है. The pressure doesn't look like it is constant. If it doesn't look like constant, then pressure के लिए which form will you use? There are only two formulas I taught you. P is equal to P naught plus rho gh and Tp is equal to rho gdh, the differential form. So in the formula there is a rho. So can you write the ideal gas equation somehow in terms of rho? dP is rho g dh. I know g, I want dh, I don't know rho. Fair enough. In ideal gas equation, if I can write that somehow in terms of rho, I can eliminate rho and I think I might get something. You will never know the answer till the end. You might always think like, oh, I might get something. So give it a try. So think from that perspective. You don't need area. Because if you have more area, you'll have more gas. So it balances out. Think, I'll give a minute more. Let's see. P is density rho. Right, Niharika. That is the thing there. So we have PV is equal to nRT. I can write V, N is mass by molecular weight. That's your number of moles. If you divide mass by volume, suddenly it becomes density. That is one. Next thing, dP is equal to minus rho GdH. Why minus? Because generally in the formula H is measured from the top. Remember we say rho GH H is measured from the top. Measured from surface or from top. But here we are measuring from the bottom. Therefore you'll get a minus sign. That is one thing. In case you forgot that minus sign, you'll get something, but then I'll tell you how to still work it out. So there we got it. So take this rho from here and dump it there. So this will be dP. This is P, molecular weight, by RT into G into DH. So we get dP by P is minus mg RT DH integral 0 to H. At 0, the pressure was P naught and P. That was ln. So ln P by P naught minus mgh by RT. Therefore, we get P is equal to P naught into e power minus mgh by RT. Now, in case you forgot the minus sign, you'll get a plus sign and you'll clearly see function is increasing. Now, you keep this in mind. In physics, at least in 11th and 12th, you will never see e power plus into something. Simple reason. If you have e power plus into something, meaning this value can go to infinity. And in physics, something can go to infinity, means it has infinite energy. Such systems don't exist in nature. You will never get e power plus into something. If you got plus, matlab you forgot something minus somewhere. Keep that in mind. You will never see this in 11th and 12th. Maybe in some extraordinary cases or some cases like, where hypothetical cases you might see, but physics may 11th and 12th, you'll never see this thing. Decent result. Again, remember, we got this result under two assumptions: temperature is constant and G is constant. In real life, even those two are messed up. So it won't be really this simple. The question was a little tough to think, but easy to solve. Clear with this? This is your KTG, everyone. KTG and fluid mechanics. Next one. Clear? Devansh, Devika, Ojas, got this? Ahana, clear? Abhinav, Sharman. Next one, going ahead. Daksha. Perfect. Next one. We have a liquid here. density rho, someone immersed a plate in arc disk. Radius r. This is at a depth h. Pressure is P naught. Find force due to the liquid. On one face of the disk. Basically one side. Meaning if generally right, Abhinav. Meaning if the diagram is confusing, have a look at my screen. It's like this. If you're looking at my screen, right? This is what I was doing. If this was the disk, my phone, whatever it is, if I immerse it in the fluid, there are two faces, right? This is one face. There is one face, front and back. Now, if I take both of them, they will cancel out, isn't it? You'll get zero. I don't want that. I want force only on one face. Is the question clear what I'm asking? A disk will have two faces, front and the back. So find the force on any one face. We need force on any one face. I hope the diagram is clear. Let's get this. So as you go down, pressure changes. So you can't directly say pressure into area here. Think it's a pretty good one. Hmm. 2r by 5. Either behind you don't know the results of something, or you got it wrong, or you're hallucinating. Something is happening. I will go with the option where you don't remember the results. You have to indicate it. That much I'm sure everyone must have figured out. Let me show you. You'll see something interesting. Listen carefully. So at a depth x, or let's call it depth y, I will take a thin slice. Now you can see as you go, the area keeps changing. Let the area be dA. This is the area of the strip. Now, what is the pressure force on the strip? Force on the strip, pressure, which is P naught plus rho Gy into dA. So force on the aft disk is integral force on the strip, which is P naught into dA plus rho G integral y dA. Now, listen carefully here. So integral y dA, I will multiply with sigma and divide by sigma. Sigma is surface density, mass per unit area. Then this will become what? 1 by sigma integral y dm. I will multiply mass and divide by mass. Then this will become m by sigma integral y dm by integral mass. Mass by sigma is nothing but area. This can be written as integral y dm by integral dm. This is dA. What is this? What is integral y dm by integral dm? Have you seen somewhere? A into y center of mass. That is your center of mass, everyone. So this whole integration, that turns out to be the center of mass thing. So now when you replace here the force on the aft disk, you can simply write this thing as P naught into area of the disk plus rho G y center of mass into area of the disk. This can be written as P naught plus rho G y center of mass into area. So this can be written as pressure at center of mass into area. So in our case, my answer would be P naught. The center of mass is at a distance of h plus, for a half disk, the center of mass is 4r by 3 pi. Area of the half disk is pi r square by 2. That is your force, everyone. If you don't know your center of mass results, you'll be gone. Didn't expect center of mass, na? What was I telling you? Every damn chapter will come. So this, if I'll just write a general result, quite a good result to remember. I will make this result even better extension. You can take actually any amoeba plate, any sheet, and if you immerse this in a fluid, and if this was your center of mass, so you can simply say the force on that sheet is simply pressure at center of mass into area of the sheet. The only thing is this is valid for constant pressure or linear functions. You cannot use this if the pressure is changing in x square or something. Constant pressure and when pressure changes linearly. It doesn't matter. You take any type of sheet. If you can somehow find the center of mass, you'll get the answer. And if you see the proof also, I simply took area as dA. I didn't even tell you what kind of strip is that, isn't it? dA was a variable. I could have taken any random shape here and I could have still got the same answer, A into Y center of mass. Have a look at the steps. So I didn't take the exact area of the disk. I took dA. So that made my life easy. I can make this a generalized result for anything. But a pretty neat technique to convert that integration to center of mass. But have a look at step by step. But this is for sheets. Now, if I give you a 3D shape, then how do we use this? We'll see that also. Any doubts on this? Right? All got this? Any doubts on this? Neat result, right? Centrum was unexpected. 5-6 years back when I did this question, I actually integrated for an half disk with an element and everything. And when we got the result, right, even I was shocked, like, why the hell did I get 4R by 3 pi? And then I tried to do it generally, and then I came up with the centrum Haskell thing. So you do figure out sometimes. Now, if you can make this even more generalized, imagine you have a piece like this, some random piece. Able to visualize how is this? Think of like this. Let's say it is your birthday and they have a cake there, and your kid sister comes there, puts the hand on the cake and removes a slice. Isn't this how it looks? Ever tried that or ever seen someone taking a cake with the hand? You put the hand in the cake and just pull it out. So some random piece there. So now look at my logic here. So if you take this sheet here, let's imagine a massless water like this, meaning you have water. In this water, you imagine an piece like this. Now this is an equilibrium, right? It's an imaginary piece, it's an equilibrium. So can I make this argument? Whatever force is acting from the left-hand side must be equal to the force acting on this rectangle, or else it won't be in equilibrium, no? Correct. So I don't care about the shape. So all this pressure that is pushing this horizontally must be equal to the force acting on this curve. So let's call this rectangle a projected area. Basically, it's like a projection. We will talk about that thing in more detail. So the horizontal force on the curved surface is pressure at center of mass of projected area into the projected area. You get it? So basically, you can find the force on this rectangle that will be equal to the force on this entire left-handed side curve. That is because there should be an equilibrium. The left side force must be equal to the right side force. And if I take some examples, this is how it looks. Suppose if I take a cone like this, let this be height h. This would be the center mass of this. This is R. So the force acting on this curve, if you see, this is how the pressure is acting. This would be the projected area here, the disk. So you can see the force, the horizontal force on the curve. Is pressure at center of mass into the area. So here the pressure of center of mass is P naught plus rho g r plus h into the area of the disk is pi r square. Makes sense. There's no need to integrate, no need to do anything, because if you actually see every point here, pressure is different, isn't it? But if you use the argument, if you consider an imaginary cone, there's a water inside, water everywhere. It is an equilibrium. That means all the forces from the left must be equal to all the forces on the right. So this is how you do for a 3D shapes. You can put a projection of that, and then you can find the force on that projection. All clear with this? Let's see a question based on this. Any doubts on this? Y direction, that we don't consider. That's why I said no, I wrote specifically horizontal force. This will only give you the horizontal force. Y direction ke liye there is a way. We'll see. So let's see based on this question. Let's say we have a cylinder. Solid cylinder separates two different liquids. And one side you have a liquid, density 2 rho, height is r, the radius. On the other side, you have a more denser liquid, 3 rho, and the height is h. Suppose if the heights are not, if there's one side height is more, what will happen? The cylinder will go left or right. So find h if the cylinder is at rest. Are you able to visualize how it is? Think of like this. If you're looking at my screen, this is like the cylinder here. You can see the water bottle. This is like the cylinder. So there's one liquid on this side and one liquid on the right side. So both the liquids are pushing the cylinder. You're getting it? So at a particular height, the cylinder will be in equilibrium. Is the diagram clear, everyone? It's a long cylinder separating two liquids, left and right. The red liquid is pushing to the left, the green is pushing to the right. Find H, height of the 3 rho liquid if the system is in equilibrium. Try, you got a minute or two. Just now I taught you, the force on a curved surface is what? You drop the projection and find the force on that rectangle. R/3 नहीं रे अंश, इतना चांस नहीं आएगा, रूट में आएगा. नहीं Jainil, that's also wrong. Let's see. No, I will try my best to draw the diagram, but listen carefully for this thing. For the red one, if you see, this is the whole curve, isn't it? Now for this, what will be the projection? You will have a rectangle like this. You will have doesn't it look like this? What is the projection for this? The projection is this rectangle, no? Height of the rectangle is R, length is L. The center of mass will be in the middle, which is R by 2. So the force due to the 2 rho liquid will be density of the liquid 2 rho. Again, remember pressure at the center of mass into area, which is 2 rho G. Height is R by 2. Area is L into R. Similarly, if you look at the 3 rho liquid, the height is H. This side is L. This is the center of mass. This would be H by 2. So force due to the 3 rho liquid will be 3 rho G H by 2 into area is L into H. We're talking about this piece here. Is that making sense, everyone? So you just need to drop the projection. So for a cylinder, if you drop a projection, you will get what? You will get a cylinder, right? This is a cylinder god. What sphere? Read the question.
Yes, like, but that was my doubt that if it was a sphere.
If it was a sphere, then what will happen? Try and tell me. Don't change the question, Ray. First do the question that I gave you. Get the answer for this. Then try in a new one. What is the point of doing a new one? It's a good fine, it is a good one. Do it on your own. That is fine. First get this one. Nah. Don't change the question. Don't confuse people. So this is F2 row, F3 row. Sphere mein what would happen? Think. You will get a part of a circle, isn't it? So how much is this guy? This guy is rho G R square L. This is 3 rho G H square L by 2. Rho G L, rho G L, H will be root over 2 by 3 R. That's your answer, everyone. Check your steps. Pretty good one. It might look easy that we solved, but because you know the result, it looks easy. So when you get a curve like that, you can just drop a projection. In this case, you'll get a rectangle and then find the force on a rectangle. That is easy and finish it off. Any doubts on this? Check this out. Clear? Next one. We can do this even, make it even better. Now listen to this concept. This is important. It will come 6 times. 6 chapters you will see this concept, projected area and projected length. So what is this projected area? Projected area is basically an area which makes an open surface into a closed surface. And let me show you how it looks. For example, look at this logic here. I have some weird amoeba shape here, right? So imagine a random shape like this, a massless shape, and put it in atmosphere. Now we know the atmosphere is going to push you from every direction. Remember, it is massless. So everywhere the pressure is constant. What is the net force? Zero, right? If the net force is not zero, won't this thing start going left and right? Means out of nowhere it is gaining velocity freely. That doesn't make sense. You're getting it? So if you take this figure, we know the net force is zero because the pressure is acting in all directions. It cancels out. Does everyone agree with this statement? If you take any random closed surface, right, it is an equilibrium. That means net force is zero. So from this we can argue that means if I can separate this into two pieces, this random curve plus, getting it, I am taking the shape C, like the weirdest one, plus, and if you take the disk. So from this, can I make an argument that whatever force was acting on this curve is equal to the force acting on that disk? So force acting on the curve plus force acting on the disk is zero because there's a net force. Makes sense? So the force on this curved surface is pressure into projected area. So in this case, the projected area is the disk. So if you put the disk there, you can make this figure into a closed figure. The only problem with this is valid only for constant pressure. Let me show you some examples. But are you getting the argument? If the net force is zero, if you cut this shape into two pieces, actually you not cut like this one, you can cut it into however you want, two pieces. The force on both the pieces must be equal and opposite. Now, why am I taking a disk? Because if I take a disk, can't I find the area easily? And I can find the force into area. It becomes easy to solve. You could have covered that hole with any kind of weird area. Answer would have been still same. So just to give an example, let's look at this. So if you have a disk and if you have a weird shape like this, or if you have a hemisphere, or even if you have a cone, for all these three cases, this is the projected area. So it really doesn't matter what is the shape as long as the projected area is same. So in all these cases, the force on the curved surface will be pressure into pi r square. You take any shape, you can just close it. But remember, pressure has to be constant. No, don't say shadow, because if you say shadow, the problem, what will happen? What if I take like this? Here, what is happening, this pressure and this pressure will cancel out. Now, basically, this area is useless. So you can say, if you want to say in terms of shadow, you can say this shadow and this shadow, they cancel out. So better way to say an area, if you put that area, the whole thing becomes closed figure. That is easy to put it. Clear? Now, can you tell me how will take a projected area for this? Instead of a full cone, what if I take an half cone? We have an half cone here, so pressure is acting like this. This is 2r, and this was height h. Now, can you find the force on that half cone? Means you cutting the cone into half vertically, and the left half में मुझे force चाहिए. How will you take a projected area for this? Again, remember the definition. Straightforward. An area, when you put that, the whole figure should become closed. Everyone is clear now what is closed and open? When you say a thing is closed, if you try to put the finger inside without crossing the the material, you can't put the finger inside. But if you have something like this, you can put your finger inside this without touching anything. That's a very layman way of defining, but okay. RHP नहीं रहा ना. No. You guys are goofing up. See properly. The force is at an angle. You'll get two components. Pressure is scalar. Force is still a vector. Think. I'll go 30-40 seconds. It's a decent one. How will you get the projected area for this? A projected area need not be always a single area. You can have multiple areas also. You just have to make it a closed figure. Let's see. So to make this a closed area, I need two projections. One, I need an half disk. Then I need a triangle. Agreed? So basically, this is the projection there. This part here, I need to close this. I also need to close this part. Now it becomes a closed figure now. Remember, your job is to make it a closed figure. So we got a triangle. So on the triangle, what is the force? Pressure. Now, P is constant everywhere. So P into area is half into base into height. This is I cap. This will be pushing down. This is pressure into area pi r square by 2 half disk minus j cap. So the force will be P into R into H I cap minus P into pi R square by 2 J cap. Is that making sense, everyone? Because if you see, look at this force here. This is at an angle, right? Iska I cap J cap दो component तो होगा ना? There are two components for it. All clear with these projections? So keep it pretty simple definition. You need an area. When you put that, the figure should become closed figure. If you need two areas, put two areas. You need 50 areas, put 50 areas. The reason why we take flat areas is because you know how to calculate the areas there, and it is easy to calculate the force. Is that clear? You could have made an amoeba like this also. You could have closed this with some weird shape like this. But I don't know how to find that area and why to make your life so difficult. So just put a triangle and put a semicircle, half disk. Clear with this? So this is all great, when pressure is constant. All this is P is constant, so it is good. But what if I give you something like this? If P gets messed up, then what you do? So let's say we have an hemisphere. Filled with liquid. Density rho. Let this height be h. Let this radius be r. So now here, if you see, the pressure is not constant. As you go down, the pressure increases. Now you can't use projected area. Find the force on the curved surface of hemisphere. Pressure is not constant. Here P is P naught plus rho gx. So P is not a constant. Therefore, we can't use projected area. Now what? Fx is 0. Fair enough. Get Fy. Question is clear, right? Get this. Let me ask you something. P naught Fy. Nay, Vihan. How did you even do that? That is force on the base, right? I'm asking you force on the upper curve. Did I say this is in equilibrium? This thing need not be on the equilibrium, right? Maybe this is resting on the ground. Listen, imagine this is your head. Perfectly shaped. Right? So now you tell me, who is exerting force on you exactly? When you say what is the pressure on your head, who is exerting this force on you? The water? The liquid, right? Which liquid exactly? Does this liquid here exert force on you? The liquid on top of your head, isn't it? Means you're only interested in this cylinder. Are you getting the argument here? The force you're getting is because of this liquid here. So if I draw the FBD of this liquid, so from the top, we have P naught into pi r square. We have mg. This will be the force due to the curved surface. And by Newton's third law, it is the same force acting on the hemisphere. Agreed? So force due to the curved part is mg plus P naught into pi r square. What is m? M is the mass of this. So this is a full cylinder minus an hemisphere. So mass will be density. The volume will be pi r square h minus 2 by 3 pi r cube. Easy, everyone. So the force acting on that, it is simply the weight of the water on top of you and the pressure. Clear? Now we can actually use this to find the vertical components, like what Vihan is asking. So if I give you some random shape like this, and let's say this is filled with liquid. So the force on that upper part, if you look at this, if someone asks you find the force on this piece, right? So the force on that piece will be only because due to the weight of this water. This would be mg. This would be P naught into area. That area has to be given. So this is the force on the upper curve. This is the force on the vertical on the upper curve. Is that argument making sense? All the force acting on this red curve is only because of this weight of the water, isn't it? So you could have taken any shape. This logic still works. Sure, everyone? Only the upper curve. We are not talking about the lower curve. mg, like this is the random shape. They'll give you something. All clear with this? Any doubts on this? Please ask me. It's a good one. There is no integration, nothing involved. You'll get it. Take a break. Come back with 7, 8. We'll continue from
Sir,
here. Yeah.
so like one last doubt is that how do we know that then on the when we have like taking fx, then how do we know that part is in equilibrium?
Symmetry like here in this case.
But sir, in the
Or
shape that you
if you given any random shape, then you can still make that argument, right? For this piece, this is the projected area. For this piece, this is the projected area. That will be same.
is projected at.
Meaning any shape, the horizontal projection is same, right?
Yes, sir. Thanks.
Come back in 10 minutes. Yeah. Let's start off next one. So we have a U-shaped container here. So on one side, we have a liquid of density 2 rho. This is L, this is L. This is liquid rho. This is L and this is L. Now, tell me one thing, is this possible? If you take a U shape like this, and if you put two different liquids, 2 rho and rho, do you think they'll balance equally? The 2 rho will dominate, right? But this can be done possible if you accelerate with a constant acceleration. So if you accelerate this container, it is possible to keep them equal. Find A. Find A if liquid is at rest with respect to the container. Cams on everyone. Get this, you got a minute. Any answers? Right, we have one answer, everyone. Like I keep saying, if something I say it is at rest with respect to the container, I'm asking to draw an FPD. Let's take this point here, A. And let's take this point as B. This was rho, this was L. So here the pressure will push with PB into area. And this was L and this was 2 rho. And this will push with PA into area. And this whole thing is accelerating. So net force is mass into acceleration. So PA into area minus PB into area is mass into acceleration. PA is what? PA is P naught plus 2 rho GH, 2 rho GL. PB is P naught plus rho GL into area. What is mass? There are two liquids here. So 2 rho area length L plus rho area length L into acceleration. P naught will cancel. This is rho GL is equal to area will cancel. 3 rho LA is equal to G by 3. There, all we did was draw an FBD. That's what I was saying. There's nothing there other than free body diagrams. Clear? Next one. So we are drawing the FBD of the horizontal liquid. And remember, the vertical direction mein acceleration won't matter. It's only rho GH. P naught is the atmosphere pressure here. All clear? Next one. Any doubts on that? We have a test tube here. This is rotating with omega. This is filled with liquid. Density rho. This is x is equal to 0 is your axis. This is some x is equal to L at a distance x. The pressure is Px. Neglect gravity. Find the difference in pressure Px minus P axis. So what is the difference in pressure between these 2 points? It's a standard result, which you should definitely mug it up. Using this result, the actual question would look something like this. So you take a U-shaped tube here, and this is rotating with omega. This is L by 4, and this is 3L by 4. And because of this rotation, the liquid will have different heights. This is H2. This is H1. Both are connected. Find H2 minus H1. You need the first question result for the second one. Get them both. Do you guys remember where we have done something like this, similar like this? Anyone remember? A rotating rod. Find tension as function of x. It has its similarities. I won't say exactly same, but try. Get the first one. I'll give you a minute for the first one and 2 minutes for the second one. Anyone not clear with the question or the diagram, please ask. Let's see. Where was this? So whenever you get a thing like this, that's what I keep saying, it's not like it is the exact same question, but you get to know how to choose elements. You take a small slice, dx. So pressure from here will be P into area. Pressure here is P plus dP into area. Think of like this. Imagine you're standing in a queue. If you're standing in a queue, what is the person in front of you doing to you? Pushing you back. What is the guy behind you doing? Pushing you front. So for this dx, that's how it feels. There is a liquid in front of you, there's a liquid behind you. Right? And with a small increase in dx, let the pressure increase by dp, and the centrifugal force is dm omega square x. So from here we can clearly see dp into area will be dm omega square x. The difference in pressure is coming because of the centrifugal force. This is dp into area, dm is rho, area dx, omega square dx. Area cancels, we get dp is equal to rho omega square x dx. This limits will go from 0 to x. Now, at the axis, we don't know the pressure. This is px. So px minus p axis, the difference in pressure, is rho omega square x square by 2. Pretty decent result. You can remember this. But remember, this result can be only used from axis to a point. You will need the result for the second part. Clear here. And then how will you find with that? You can do that. That also works. You are taking the midpoint of it, centrifugal force. It's a linear function, so it works. Now can you do the second part? Now how will we do this? I wrote dx twice. Uh, let's get this. You got a minute. Consider this point is A. Now remember, you can't directly use the formula from A to B. You can use it only from A to axis and B to axis. There, I gave you the idea there. What is PA? P naught plus rho g H1. What is PB? P naught plus rho g H2. You have everything you need. Get it? Let's see. So if you take the pressure difference here, PB minus P axis is rho omega square. The formula is x square by 2. So rho omega square by 2. 3L by 4 whole square. PA minus P axis is rho omega square by 2 L by 4 whole square. Subtract them. You'll get PB minus PA is rho omega square by 2. That is 9L square by 16 minus L square by 16. And PB minus PA is rho g H2 minus H1. P naught plus rho g H2 and P naught minus rho g H1. This is rho omega square L square by 4. There we get H2 minus H1 omega square L square by 4g. Clear, everyone? So remember, you can't use the formula directly from A to B. It is always has to be from the axis. Or you got to change the limits, what here, but you got it. Clear? This is again one type of model there. Next one. Turn in the page. So we got a square plate here. Sidle. On one side of the square plate, there is a liquid. Now, if you look at this, the side view, how will the liquid act on this thing? Does the force the same everywhere? As you go down, isn't the force increasing? Means the bottom part of the wall will experience more force than the upper part. So in order to keep this at rest, someone applied an F external at a distance y from the top. Getting it? So a square plate is blocking water. Blocks liquid as shown. An external force acts at a distance y from the top to keep it at rest. So the first thing is, how much force should you apply? If you apply less force, the plate will move. If you apply too much force, the plate will go towards inside. Find F external and Y. And how much, where should you apply? Think about it. If there is more torque at the bottom, the tendency of the plate is to rotate like this, isn't it? So if you apply the force on the top, then the plate will come out. If you apply the force at the bottom, there is a chance the plate will rotate inside. Right? So there is a particular spot where should you apply. Its gravity is there, Nare God. This is just a liquid column, right? It's like a wall of a dam, you can say. Gravity is there. This is vertical. Imagine your room is filled with liquid. This pressure is not increasing with depth P naught plus rho g h. So if you see, right, if whenever someone wants to construct a dam ka wall, this is a pretty bad idea. You don't construct a dam ka wall like this. You don't build a wall and put sand like this. Because as some time passes, the wall will eventually become like this. So you know how they build a dam ka wall? They build it like this. And you know when is the dam more stable? When it is full. The more water the dam has, the more stable it becomes. Reason, see, these are pretty interesting structures. Dam is one. The more stress you put, the more stronger it becomes. As you put more and more water, the pressure increases more here. So the pressure is less here. If the pressure is more, there is more normal reaction. If there is more normal reaction, there is more friction. Getting it? That friction will stop the dam ka wall to go, from moving forward. So this is a self-sustaining thing. The more water you keep, more normal reaction you have, and more stable the dam becomes. You can store more water. So the danger of the dam is this: if it becomes too much water and if it overflows from here, then we have a problem. This water is going to fall here, and because of that, you'll get soil ka erosion, and the dam ka walls get damaged. The water is less, so then there's no force only to push it. This is the walls of a dam. Let's get this. So how much force should I apply to keep this plate at rest, and where should I apply? So force for equilibrium and position for torque. Get this. You got 2-3 minutes. Standard question. Force is actually easy. You can actually take pre-center of mass and to finish it off. Remember? Pressure at center of mass into area. That would have been easy there. But let's integrate anyway and see. So we take a small strip here. Of thickness dx at a depth x. So if you look at the side view, so on this small strip, the force here is pressure P naught plus rho gx into area. From outside also there's an atmosphere P naught into dA. So the area for this strip dA will be, this is the length here, L into dx. So force on this one strip, P naught will cancel, rho gx and dA, which is rho gx L dx. The force on the plate will be integral force on this each strip, rho gl integral x dx from 0 to L, rho gl cube by 2. Check. That is the force on the plate. You could have got this from center of mass also. Where is the center of mass? Middle, right? So the pressure will be rho gl by 2 into area is L square. There, you got the same answer. Pressure at the center of mass into area. It doesn't work for torque though. Now, what is the torque due to the torque on the strip? Torque on the strip is the perpendicular distance x into force on the strip. That would be rho g L x square dx. So the torque on the plate will be integral torque on the strip. That would be rho g L integral x square dx from 0 to L. This is rho g L power 4 by 3. Now for equilibrium, you are saying this must be equal to F external. This must be equal to torque external. So torque external is nothing but y into F external, which is rho g L power 4 by 3. And F external is rho g L cube by 2. There, y is equal to 2L by 3. The force not in the middle should act actually a little below. Kind of makes sense because there is more force at the bottom, there is more torque. Other steps clear, everyone? So you should apply this much force and you should apply here. You should apply 2L by 3. If you don't apply this much force, the plate will move left and right. There's a translation. If you don't apply at this position, you'll have a rotation. So when they say equilibrium, you're talking about both the translation and rotational equilibrium. Check this out. Clear, everyone? Any doubts on this? Let's see. Next thing. There, that is few of them. Then the next thing is the barometer. So what is this barometer? So this is how we construct this. Consider a 1 meter long glass tube. Filled with mercury. And then invert it into a trough of mercury. Trough is nothing but a cup. we observe the liquid level drops, creating a vacuum at the drop. Meaning, this is what we do. We take a 1 meter long tube, we fill this whole thing with mercury, make sure there are no air bubbles. So normally what they do now, they fill with mercury and they tap the whole thing. They just hit it a few times so that if there are any air bubbles, they will escape. There should be no air bubbles. Then what you do, you take this, you take a small bowl of mercury and then you invert this inside. All this is mercury. And then you'll observe this mercury level actually drops. And in this process, it creates a vacuum here. Think about it. If the liquid just comes down, there is nothing to occupy on the top, right? So this is how we can actually measure the atmosphere pressure. We'll see that. And at this level here, we know the pressure is P naught, atmosphere pressure. This experiment actually became famous, for creating vacuum. During 1800s, people used to think only devils can create vacuum. Like, okay, they had their own concepts of thinking science, but people believed only devils can create vacuum. So this guy Pascal, right, was actually became more famous for creating vacuum than actual barometer. We humans are always like that. We are, we are more interested in the something else. Ever seen kids ka Kinder Joy? They're more interested in that bloody toy inside than the actual chocolate. So it's like that only. So why is that liquid coming down? So if you take this liquid here, if you draw the FBD of the liquid, here the pressure is 0, so there is no force. Here we have mg, and here we have P naught into area. So P naught into area is mg. P naught into area, mg is nothing but rho, density, height into g. There we get the formula, height is equal to P naught by rho g. So the atmosphere can balance only this much amount of weight, and that is the reason it comes down. We will see how much is that. Now, while doing this experiment, you have to be a little careful with few precautions. First one, by chance, if you let any air bubbles present, or if there's some air escapes inside, you won't get vacuum on the top. That means the height will be less than the normal. If there are air bubbles, it won't be vacuum on the top. So the liquid will actually go down even more downward. Second, we prefer to use mercury. We don't use water because if you use water, water creates a vapor pressure. Right? If you have vacuum, some of the water will become a vapor and the top there won't be vacuum again. That's the reason we don't use water also. So we prefer to use a liquid which don't create any vapors. We will see, and there's another reason why we don't use water. If we use water, there will be vapor pressure. Which you won't be able to calculate. Different temperatures have different vapor pressures. You don't want to get into that headache. Mercury is safe in that sense. The experiment is clear. Now let's see if you try to find this value of the height. So we got H is equal to P naught by rho g. Definitely remember this. Now for mercury, H will be P naught is 10 power 5, mercury is 13,600, G is 9.8. This turns out to be 76 centimeters of mercury column. This is how we got that result, like 1 P naught is 76 centimeters of mercury column. Instead of mercury, if you had used water, this is 10 power 5 and water is 10 power 3 and 9.8. This is again approximately 10 meters. That is another problem. If you try to use water in a barometer, you need 10 meters long pipe. So you don't use water. So mercury, something more denser, is better. This is the formula there. Remember, there's a G in the formula. That means if we keep this inside a lift, there'll be G effective and all that stuff. Gravity does get affected. So let's say we have a barometer like this. Now tell me what happens in this case. Let's say case 1. If you make a hole here, what happens to the height of the liquid? Suppose if you make a hole here, now what happens to the liquid here? The barometer is there, it is an equilibrium. Now you made a hole at the top, and if you have made a hole at B, what will happen to the liquid? What will happen exactly with the whole thing? Let's see. The moment you make a hole here, what will happen? The air will rush inside. If the air goes inside, what will happen? Vacuum will go off. As the pressure becomes P naught on the top and the pressure is P naught at the bottom, there's no one to stop you. Liquid level go down. The whole reason why the liquid is being lifted up is because of the difference in pressure, isn't it? P naught A, and this was 0. If the pressure is P naught and P naught on both the sides, they will cancel out. Mg will be 0, isn't it? What will happen here if you make a hole at B? B is interesting. Will you get a fountain? At this point, what is the pressure? P naught. So if you're going at a height, the pressure here will be P naught minus rho GH. So pressure is actually less, isn't it? So if you make a hole, air will enter inside. Because the pressure outside is more. Pressure outside is greater than pressure inside the hole. Then what will happen? These air bubbles will go up. So vacuum goes off and the liquid comes down. Air enter inside, bubbles float because they are less denser. So you'll not get a fountain. If you want a fountain, what should you do? Make a hole at A and B at the same time. Then the pressure here also becomes P naught. Here also P naught. All this extra liquid, right, will start going down and some of it will come out through a fountain also. You'll get both. Just some theoretical questions if you make a hole. Is this clear, everyone? Clear? Let's see our question. Any doubts on this? Clear ना वो just निकल Soham Parth. Great. Next one say. We have a liquid. You took an open pipe. Open end on both sides. This is mercury. This is 50 centimeters. This is also 50 centimeters. Outside the pressure is P naught, which can be treated as 75 centimeters of mercury column. Then what you did, then you sealed this container. You closed it on the top. This is still 50 centimeters. Nothing changed. You just sealed it at the top. Then what you did, you pulled it out. You pulled it out by 75 centimeters. Pulled out by 25 centimeters. In this process, something happened and the liquid level actually went up for some reason. You need to figure out why it went up. Liquid level rises by X inside the pipe. When it is pulled out by 25 centimeters. Remember, the top it is sealed now. Find X. Question is clear? You took a 1 meter pipe, half inside, half outside, right? So initially there was air, half of it was air. You sealed it. So air got trapped inside. Now you pulled out, something happened. And that liquid, it went up little above inside that. So find X. In this entire process, assume temperature is constant. Assume isothermal conditions. They will sometimes not give that, but that you need to understand. Think, I'll give you 2 minutes. Remember, pressure is given in terms of length of mercury column, so you can use that in terms of pascals. Anyone not clear with the diagram or the question, please ask. Question is clear, go ahead, you got 2 minutes. Let's see. What is happening? Anyone figured out what's happening? When you sealed it, the air which was there, when you pulled out, it got expanded, right? So if that volume expands, what will happen? Pressure will decrease. So you created a low pressure region here on the right. Because of the low pressure, liquid went up a bit. Is that making sense? So let's see. So here the pressure was P naught. Here also it was P naught, even though you closed it. Here the pressure is P dash. This level ka pressure is P naught. So we are using P1 V1 is equal to P2 V2. So initially pressure was P naught. Area length was 50 centimeters. Let's keep it in centimeters everywhere. P2 is P dash. Area, this was 75 minus X. So, and remember P naught, you can take it as 75 centimeters of mercury column. So this is 75 into 50 is equal to P dash into 75 minus X. This is equation 1. Second thing here, you can see from here, P dash plus rho mercury Gx is equal to P naught. And what is P dash? P dash is P naught. P naught is how much again? Rho G 75. That is the meaning of that, everyone. P can be written as rho G. Rho G 75 minus rho Gx. This is equation 2. Take this and substitute here. So you'll get 75 into 50. This is also rho G 75. So rho G 75 minus x ka whole square. You're done. 75 minus x whole square is equal to 75 into 50. Solve this, you'll get x answer. Is that making sense? Because of this small height of the liquid, the pressure here will be P dash plus rho Gx is P naught. The pressure at the surface level has to be P naught. This pressure has to be P naught. Any doubts on this? So sealing on the top was important. Because of that, the air got expanded, pressure dropped, and the liquid went up. Next thing. So that is one thing about a barometer kind of thing. This is another way of asking questions. Then Pascal's law. So what Pascal's law says is the increase in pressure at a point is transmitted undiminished throughout the fluid and to the walls of the container. So if you increase pressure at one point, it just doesn't stay there. This will actually transmit everywhere throughout the fluid. And to the walls of the container. So did you ever notice this thing? Let's say if you're sitting in a bench of 3 people and suddenly the fourth person tries to come and sit here. Don't everyone in the bench feel the pressure? It's not only this person in the corner, everyone gets stuffed actually. If you ever been in a local train, you must have felt this. When the compartment is fully jam-packed and one person tries to enter the door, literally everyone feels the pinch. At least, in case of humans, right, we have some gaps between us, so we adjust. But in case of molecules, when they're tightly packed and you try to push one more molecule, everyone feels the pinch from beginning to the ending. So that's what it is saying. If you increase pressure at one point, it just doesn't stop there. It will spread everywhere. So if I take a simple thing, let's say if you take a sealed container, fully filled. Let's say this is point A and this is point B, and let's say this height is h by 2 and this height was h. You can clearly see pressure at A is rho gh. Since it is sealed, there is no atmosphere. Pressure at B was rho gh by 2. Now, all you need to do is put one small hole. So in the container, if you make one hole here, the atmosphere is pushing here with P naught. Now suddenly pressure at A becomes P naught plus rho gh, means whatever you had initially plus this, PB also becomes P naught plus rho gh by 2. Did you see? Pressure everywhere increases by P naught. That one small hole will bump up the pressure everywhere inside by P naught. So that's what Pascal's law simply says. Has a lot of practical applications. Every hydraulic thing that you're seeing, right? Ever seen crane lifting, right? Any objects that are, all these motions, your car brakes, all these are based on hydraulics. The advantage is this. Think about it. Let's say you want to send power from point A to point B, but unfortunately, there are a lot of obstacles. So you need to send the power like this. Do you think you can use some mechanical system to send power like this? Look at your cycle. When you're pedaling, the power goes from the pedal to the back wheel through a chain. It is straight, isn't it? So there's no problem. But if I have to send like this using a conveyor belt or a chain, problem with these things, right? Whenever the rods or something bend, there is a chance the materials will deform and you will have a lot of loss of energy. There are a lot of issues with this. But look at this thing, what it says. All you need to do is increase pressure at point A. The pressure will pass through this and reach B without getting undiminished. So that was the reason. So whenever you're going on a car and you press the brake gently, the whole car stops, right? So how are you generating the pressure to apply brakes on the tires? Just by pushing the pedal. There's an oil there, brake oil we call it. Movies mein they show na, hero is going, the oil leaks, the brakes fail. That is a common story that you see in normal standard movies. So there is a brake fluid there. When you press it, that hydraulic pressure pushes the brake. Why all that? We have something called pneumatic drills. If you ever seen this road car works, they have this big jackhammers, drilling the road. Even better example, ever been to a dentist and got your teeth drilled? So if you see the machine they use, it's a pneumatic drill. And next time observe this, when you go to the dentist, right, you will hear a sound there, air tank ka sound. Barrrr karke. So actually in the dentist office, there's a small air tank. You will hear the same sound again in a tire shop. So when you're sitting on that chair, right, there is a pedal below that chair. So the dentist, when she's operating the drill, she presses that pedal and this drill starts working. She wants more, force, then she will press the pedal more. Did you ever think about it? The buttons, where are the buttons for that, drills? It is near the pedal. She's pushing the pedal there, and that is actually changing the pressure. So even before your operation starts, if you observe next time when you go, right, they fill up the tank first. So they have a small air generator which is filling up the tank to generate the pressure. So all these things, right? Your drills, the cranes, these hydraulic brakes, all this works on this Pascal's law. The disadvantage is this. All you need is one small hole here. The pressure becomes P naught. The whole thing will stop working. The advantage, you can send the power undiminished for a kilometer, but all you need is 1 millimeter of a hole and the whole thing is gone. So you always have, you're getting something, you will have always some drawbacks. So we have something called an hydraulic jack. So this is a thing which they use in these garages and all to lift heavy objects. So this is how it goes. So let's say we have a piston here, area A1, we have a piston here, area A2, and let's say this full thing is filled with a liquid. And let's say if you apply force F1 here, at this point, the pressure will be F1 by A1. So from Pascal's law, we know the same pressure will get transmitted here. So this will be delta P into A2. This will be balanced by F2. So from here we get F2 will be delta P into A2, which is F2 is F1 into A2 by A1. It's a force multiplier. You can use this as a force multiplier. So if A2 by A1 is 10 times, then you get force F2 is 10 times F1. You can put 1 kg and you can lift 10 kgs with this. You can use to lift heavy objects using small weights. But what is the catch? Like I keep saying, you get something, you have to lose something there. The catch is if you try to conserve volume, so if this guy goes x1 down while pushing, and if this thing goes x2 up, we get a1 x1 is equal to a2 x2. So we get x1 will be x2 will be a1 by a2 x1. That means we will get x2 will be x1 by 10. So if that thing moves 1 meter, you only move 10 centimeters. You get 10 times force, but your displacement becomes 1/10. And that kind of makes sense because in a hydraulic jack, you can't create any new energy. So if you look at the conservation of energy, the work done is force into displacement. So this is F1, X1, F2, X2. Since the energy is constant, if you get more force, you are actually sacrificing displacement to get more force. Is that making sense? If I get 10 times force, I have 1/10 of a displacement. The product is still same. So in a hydraulic jack, you don't create any energy. It's constant. Clear, everyone? That's a simple conch question there. There's nothing much on this. Any doubts on the hydraulic jack? Clear? One last small question. Let's wrap up with that. So we have pistons here. So these are walls basically filled with liquid, filled with. So all pistons have area A. Now what you're doing in the first one, you're pushing with 4 forces, 4 pistons. This point is A. Second case, you're pushing with 2 forces. This is B. Here, there's only 1 piston, C. Arrange the pressure at ABC in ascending order. Each point has more pressure than the least one. Now, do you remember this thing? Let me ask you this just to remind you. We have a rope here tied to a wall, and we have a rope here, and someone is pulling with 2 forces. How many forces are acting on the first rope and the second rope? 2, right? Both are one and the same. You just get an illusion that there is a wall, but remember, wall is also pushing. So in both the questions, all these 3, let's try to draw the FBD of the liquid. If you draw FBD of the liquid, for example, liquid C, you will notice, fair enough, there is a force here, but you're forgetting there's also Volkov force now. And because it is in equilibrium, this is also equal to F, isn't it? All the 3 liquids are identical. Just imagine the situation. If I don't apply this force here, what will happen? Will the piston be there? It will fly out, isn't it? So basically, this force is simply playing the role of a wall, na? Are you getting the difference? It gives you a feeling there are four forces here. There are two forces here. There is one force here. God, but you're forgetting there are also three Volkov forces, na? There are also four forces here. There are also four forces here. Is this making sense? So applying a force on a piston and keeping it at rest is as good as a wall at rest. There's no difference. Then how do you find the pressure? So if you just draw the FBD of that, remember how to find tension? We cut there and get this. So this will be PA into area. So pressure at A is F by area. Meaning everything is the same thing. If you take this and if you take this is F, this is F. This is PB into area. So take any one piston. This is PC into area. This is PB. This is PC. All are equal. It just gives you an illusion there are four forces, there are two forces, there are one force. But in reality, in all the three liquids, there are four forces. Is this clear, everyone? Simple? Easy one. But people get trapped. They see four forces and then pressure must be more. This is just like, the horse pulling, one horse pulling the rope and two horses pulling the rope. It doesn't matter. The one horse is just a wall there. Clear with this? So that is about the Pascal's law. That is about pressure and stuff. The next part of the chapter is, Archimedes principle, buoyant force. That's a good one. Again, we have more varieties on that. So we are still doing statics. Things are still at rest. The next class, when we catch up on Tuesday, we'll continue with that. But you have an idea about the Archimedes story, right? The Eureka thing. You know what Archimedes is actually famous for? Not the Archimedes principle. This guy was actually famous for making war weapons. He's a military engineer. Right? King used to pay him a good amount of money for making war weapons and all. One of his famous weapons is a death ray, which is a concave mirror. So during that time, right, when Archimedes was there used to be 5 cities in that Greece, Athens, Sparta, and all these things. And that time there was no PUBG or Facebook and also Instagram. People are bored. So what they do? Like, let's go for war. If you actually go and read all human histories, right, we have been always like that. You have nothing to do, we start going wars. Right? So that is how it has been. So people used to fight wars, and Athens was little weak where Archimedes used to stay. So, but this guy used to make brilliant stuff. So one is the death ray, which is a concave mirror. So imagine, right? You are sailing a ship to attack the city, and you're putting your concave mirror and focusing on the sail. Out of nowhere, suddenly the sail catches fire. And few days before, you spread rumors in the city that sun god Apollo is protecting the city. Anyone tries to attack the city, sun god will punish you. And you say, oh, this is all bullshit. And you take your ship to attack, and suddenly your sail catches fire. What is the first thing you think of? Shit, sun god is punishing, let's run away. So you need not always have a powerful army. You can always have a psychological warfare also. Then let's go and attack him in the night. And this Archimedes, somehow I think they found an oil deposit, right? They made catapults and they used to throw these oil fires, onto the ships. Now, on a ship, when in a water, when there's a fire, what is the first thing you do? You take water and put it on a fire. And generally it stops. But what happens with an oil fire? Oil floats and the fire continues. It's called hell's fire. And now you spread one more rumor. The king of hell, the Hades, is protecting the city. So it's a damn psychological thing. You just keep messing up. The story goes like that. And then the king used to pay him a pretty handsomely good money for making weapons, not science and stuff. Science was his passion. He was figuring out stuff, but primarily was getting paid for weapons. It is like Tony Stark was always, more cool than Hulk. So he's more famous military engineer. And then one day the story goes, the king gets a beautiful crown made of gold. But, if you make pure gold, it is always pretty soft. So you have to add some copper. So gold, so the king was a little, suspicious, like maybe the goldsmith stole some gold. So he calls up Archimedes and says, "Hey, Archimedes, this is my problem. Don't destroy the crown, but somehow figure out how much gold and how much copper is there." Archimedes is like, "What the hell, yeah? This guy has no work," but you can't say that to the king. "Okay, sir, we'll see what can I do." And this guy was scratching his head, what the hell to do? And then the story goes, he was, in a public bathtub, and then something happened. Then he started running on the roads, Eureka, Eureka. Matlab, I got it. That's the thing. We will see what is that story and how did he actually figure it out. And as the story progresses, one day finally Athenska walls were breached. The enemies have entered. So one of the soldiers goes to the library and he sees Archimedes there sitting and doing some work. And this is again written by one of the enemy general in his book, it seems. I read it somewhere. And the soldier says, get out from here. We are attacking and all that. And Archimedes like, get lost from here. I'm busy with my work. The enemy soldier gets pissed off, takes his spear, kills Archimedes, and goes off. So that is how Archimedes' story ended. So the enemy general actually feels bad. He wanted to hire Archimedes as his military engineer, but the soldier has killed him. So that is a regret, which was written in one of his book or something like that. So that is the story so far. That is how we ended up. So we will see more about this thing on Tuesday when we catch up. So we'll wrap up with this. So any doubts, anything you can stay back and ask, or else you're free to leave. And there's a test online till tomorrow. Make sure to give. So any doubts, anything, stay back, or else you're free to leave. I'll see you on Tuesday at 5:40 as usual.
We're on page 55.
Page 55. One segment. Just let me stop this recording.